This is active chemistry, problem number 5 from the hydrolysis of salts homework assignment. In this problem, we're given some pKa values for various acids and asked, in which of the following acid-base reactions will the reverse reaction be favored? So that's another way of saying, will the equilibrium constant be less than 1? And so as we look at these problems, right, every problem has an acid reacting with a base, forming a conjugate base and a conjugate acid. So what we need to do is we need to compare the Ka values of the two acids to see which one of them is the weaker acid. And that will help us determine to which side the equilibrium lies. So we have these Kas, and we know that pKa is equal to the negative log of the Ka. So the Ka values, if we could make a table here, the Ka values are simply for this one 10 to the negative 5, and 10 to the negative 5, and 10 to the negative 9. All right, and so forth all the way down. So I want to break apart, I'm going to take a look at each answer choice and talk through those, put the Ka values in with the acids so that we can look at which one is the stronger acid, right? Which one will dissociate more, which one will dissociate less. So as we look at answer choice A, the Ka for HCN is 10 to the negative 9th. And the Ka for water is 10 to the negative 16th. All right, so the weaker acid is going to hold on to its proton more. Okay, so in that case, we can clearly see that water is the weaker acid, so it will hold on to the proton more, or I guess we could say will dissociate less than HCN will, and that is going to make this equilibrium lie to the right side. Right, so here we'll favor products. Right, again, that H2O is going to hang on to that proton. The other way to look at this, perhaps, might be to look at this and say, hey, that's a strong base. And strong bases are really good at holding on to protons. Right? That's kind of their job, to grab protons and hang on to them. And so simply the presence of that strong base is going to drive this reaction to the right. If we look at B, again, we have our Ka values that we're going to get from the table, 10 to the negative 5th. And then for HCO3 minus, we are 10 to the negative 10th. And again, we see HCO3 as the weaker acid. That means it's going to dissociate less, so it will hang on to its proton more. Now, we don't have a strong base, so we can't look at it from that perspective, but we might be able to calculate the Kb values for each of those. In fact, we could, if we wanted to. We could calculate the Kb for this because we know it would be Kw over Ka, and that would be the Ka for HCO3. So that would be 10 to the negative 14 over 10 to the negative 10. And here we would have, again, Kw over Ka. This time the Ka is from the acid on the left side over 10 to the negative 5. All right, and we can see that the stronger base then is the carbonate ion, again, pushing this equilibrium to favor the products. Now, remember, in the original question, we are finding out in which one will the reverse reaction be favored. So far, we haven't found that one. So we'll look at C, where our acid is 10 to the negative 16th. That's a pretty weak acid. And the acid on the other side is 10 to the negative 9th. So our weaker acid is here, so that means it will dissociate less. And so the reactants are favored in answer choice C here because the acid there is the weaker of the two. If we look at D, we are 10 to the minus 16. And so you might say, uh-oh, that's the weakest acid in the list. However, again, we have a strong base here. And that strong base will drive the equilibrium to the right. Well, water is the other acid. It's also 10 to the minus 16. Right? And so maybe this one is, I guess we could say, sort of equal on both sides, not really favoring either reactant or product. I guess we could even go as far as saying that this base and this base are equally strong. If the acids are equally weak, which based on their Ka values they are, then the bases must be equally strong. And so perhaps the equilibrium constant for this reaction is pretty darn close to 1, right? Assuming the Kas are all 1 times 10 to the negative 16 and the Kbs are the same. So let's take a look at E. E, we have HCN, 10 to the negative 9, and NH4 plus, also with a Ka of 10 to the negative 9. So those acids are equally strong or equally weak. And so neither one of those is able to push the equilibrium one way or the other. And so maybe again, we have an equilibrium constant here equal to 1. I hope this was helpful. It's a long problem to work through, but once you kind of know what to look at, it gets a little more straightforward, I think.